one last thing. We didn't find our critical points. Let's set our first derivative equal to 0. This is pretty easy. Come on. All right, so of course it's going to be 0 where the numerator is 0. So we have 0 equals negative 7x squared plus 21. Let's, not really a factorable one here. All right, so let's just factor out the negative 7. So 0 equals negative 7. So we have x squared plus 3. We can divide both sides by negative 7. So we have 0 equals x squared plus 3. Right? We'll subtract 3 from both sides. We'll just solve using square root. Oops, excuse me, not plus 3, minus 3, minus 3. Minus 3. All right, so 3 equals x squared. That means x is plus or minus the square root of 3. All right, so this is one critical point. We have, and that's because our first derivative equals 0. We have a second critical point at 0. Right? So also x equals 0 is a critical point because our first derivative is undefined. All right, so let's solve the second one there. And again, we're going to just set 0, our numerator equal to 0. So 0 equals 14x squared minus 84. We'll just, we could factor out the 14. I think 84 is divisible. Yes, it is. All right, so that would be, factor out the 14. X squared minus, so 84 divided by 14 is going to be 6. All right, so that means 0 equals x squared minus 6. And that means 6 is x squared, and that means plus or minus the square root of 6 is x. So there we have 2 more critical points. Those are our possible inflection points. That's our critical point because our second derivative is equal to 0. And again, we have another critical point. Our second derivative, and the other one is at x equals 0. And that's because our second derivative is undefined there. Gee, why? Wonder why. Maybe it's that giant vertical asymptote. So there, now we've got our critical points. We've got positive and negative with square root of 3, negative square root of 3, square root of 6, and negative square root of 6. And actually, so here's our sign chart, and if you notice, I've divided this into intervals. Maybe I will just go through this in class. Go through this really quick now, because I think you've got it all in your notes and got it graphed. All right, so here are my x values. All right, so I've got x less than negative square root of 6. That was the smallest critical point, and that was where our second derivative was 0. Right, so at negative square root of 6. Our second derivative was 0. Right, and then we've got from negative 6 to negative square root of 6 to negative square root of 3. That's where we had a critical point, but for the first derivative. Right? So I kind of summarizing all the information on one sign chart. You can do it this way, or you can do it as 2 separate sign charts. All right, so then I have another interval from negative square root of 3 to positive square root of 3, because at the positive square root of 3, my first derivative is 0. And then lastly, I have interval from negative 3 to, square root of 3 to square root of 6, because I have a critical point for the second derivative. The second derivative is 0. All right, so now if we, I don't have the functions up here, they're on the other page. But if we plug into our functions into the, if we plug into the first derivative and the second derivative, we can find the signs and see what's happening. All right, so let's look at the first derivative. So I'm looking for values that are less than the square root of negative 3. So for instance, 2, negative 2. All right, so if I were to plug negative 2 in, so if you look back at the function, probably should have written it down over here. So if we plug in negative 2 into the derivative, right, we're going to have a we're going to have a negative number because the 7x squared is going to be larger than anybody else there. All right, so that's going to give us a negative number, right, and so forth. So I know you can plug into a function, so I don't think I really need to plug into the values back into the derivative. You can just trust me on the signs here. All right, so our second derivative is negative. All right, so that means that we were decreasing and then increasing. And my little thing here. So we were negative, and so I'm trying to figure out my arrows down here. Oh, I think I'm looking at concavity, not increasing, decreasing with my little arrows here. I forgot why I drew them in. So we are if our first derivative is negative, our function would be decreasing, right? And then we have we have a critical point, and then our function is increasing. So this would be a relative extrema, and here we can see that this is going to be a relative minimum. And I probably shouldn't write that in the column for the second derivative. So this right here, oops, I don't want to do that. Here. It's kind of hard to write on this chart. So anyway, see what happens? I get that. I don't even know how to get rid of that. So anyway, I'll figure that out later. See, I don't even know how to get rid of that. So I think I'm stuck with that there. So ignore this. I guess I should have ended this podcast. We're having issues. Ignore the little thing that says minimum. I forgot it's really hard to write in these boxes. Because that goes with the negative square root of 3. That one's the minimum. And if we plug it into the function, that value would be negative 14/9 square root of 3. So that's our relative minimum here, is at negative square root of 3, negative 14/9 square roots of 3. We have a relative minimum there. All right, and then for values in between negative square root of 3 and square root of 3, we're positive. For values greater than square root of 3, we're negative. So that means at square root of 3, we have a relative maximum, and that value was the square root of 3 and 14/9 square root of 3. All right, and then we're done with our first derivative. So for our second derivative, we had, and then of course the 0 really is not a critical point for anybody. It's a vertical asymptote. So that one we can't evaluate at all because it's a vertical asymptote. It's not really, it's not an inflection point, and it's not a critical point where we have an extreme value. All right, so if we look at our second derivative, we had a critical point at negative square root of 6 and the square root of 6. All right, so negative square root of 6 for values less than negative square root of 6, the second derivative was negative. For values greater than the square root of 6, we were positive. We were positive, and then we were negative again. I didn't seem to put any value in here. I didn't put positive or negative in here for that, but I see concave down, concave up. Oh, I use those values over here. All right, so our second derivative here was, we went from negative, we were concave down, to, I guess that's what my arrows are, to positive, concave up. All right, so we do have an inflection point at negative square root of 6. That point is negative square root of 6, 1. And then again, we have a change in our signs for the second derivative at the square root of 6. And so that inflection point is the square root of 6, 1. So those are our critical points along with our x-intercepts and our asymptotes. And so let's take a look at this particular function. Oh, let's read through our justification, and then we'll look at the function very quickly, which is in your notes. So for x less than negative square root of 3, our function is decreasing because our first derivative is negative. There's a local minimum at x equals negative square root of 3 because the first derivative is negative from negative infinity to negative square roots of 3, and positive from negative square root of 3 to square root of 3. For x between negative square root of 3 and 3, our function is increasing because the first derivative is positive. There's a local maximum at x equals square root of 3 because our first derivative is positive from negative square root of 3, square root of 3, and negative from square root of 3 to infinity. For x less than -6, our function is concave down because the second derivative is negative. There's an inflection point at x equals -6, at negative square roots of 6, because our second derivative is negative from negative infinity to negative square root of 6, and positive from negative square root of 6 to 0. From negative square root of 6 to 0, our function is concave up because our second derivative is positive. There's an inflection point at x equals the square root of 6 because the second derivative is negative from 0 to square root of 6, and positive from negative square root of 6 to infinity. Right? And so because our function is, our second derivative is positive from negative square root of 6 to infinity, the function is concave up. There's also a vertical asymptote and a change in concavity at x equals 0 as well. So we changed concavity. Notice we're concave up and concave down, but 0, of course, is not an inflection point because of the asymptote. And so here's the graph. And it looks like that. All right, so there's where I plugged into the values and I got decimal approximations so I could graph it. All right, so we have that vertical asymptote at 0. So our domain is negative infinity to 0, 0 to infinity. We can't include 0. Our range is all real numbers despite the horizontal asymptote that we have as we go, as the function heads to infinity and negative infinity. It does cover every other y value, including 0. And so there we can see we have our relative max, our relative mins graphed. I have them over there on the side listed, and then our change in concavity. So one of them occurs right at the asymptote. You can see we change from concave down to concave up to concave down. And then we have another change as well in our function at the square root of 6 and negative square root of 6. You can see we kind of change from positive to negative. And hopefully you can see that in my graph. You can see that we change from concave up over here to concave down over here. And the same thing. We're concave down, now we're concave up. So we have an inflection point. All right? And it's about, well, it was at the square root of 6. So it was roughly here. Right? So a little bit more than 2. It's roughly here. And there's our graph. All right, so that's where I'm going to end, and we're going to look at using information to graph. All right, so we finished this one. Bye for now.